Hey, thanks. All right. Yeah, thanks for having us. I'm glad to be here today. Today we'll be talking about our new work, Decision Transformer, Reinforcement Learning via Sequence Modeling. I'm really excited to share this and about this direction. So the main question we're interested in this work is looking at the gap between what current RL practice is doing and what more mature data-driven fields like in NLP and vision are doing, and what we need in order to overcome that gap. So namely in NLP and vision, we have these large models, we pre-train them, and then we publish our BERT to the web, and then everyone can fine-tune the same model. And this leads to really powerful models which learn new skills quickly. However, in RL, this is generally not the case. We have these much smaller models, they're single task, they don't necessarily fine-tune well. And what we really want to do is try to overcome this gap in order to advance RL as a field. So to do this, we're going to propose a decision transformer. And I'm going to try and motivate why we care about this problem and why the transformer is a natural solution here. So first, let's think about what we want in robotics and a learning algorithm. So we have some robots we care about. We want it to act in the world. So there's some ways we'll train it. First, we have some data that we train on. It can be offline, online, doesn't matter too much. But there's some limited interaction data. Also, we have the robots, and we want to have it understand the world visually in order to interact with it. And ideally, it would also understand language so that as humans, we can command the robot easily. All of these are like different modalities coming with different challenges. And ultimately, we want to use all these sources of data to train the robot in a data-driven way. However, this is pretty non-trivial. If we think about augmenting the robot with vision or language understanding, these are actually by themselves fairly well-known problems with pretty good solutions. Namely, nowadays you can pretty much just use a transformer for either one, for vision or language. And we've seen many times that this can give pretty impressive results. With the advances in GPT and BERT, you can just take these models online and fine-tune them on your task. Vision Transformer shows really strong results on ImageNet and such, as well as the new models Clip and Dolly, which are multimodal, which get really impressive results on these tasks requiring both language and vision understanding. These are really nice models. They are multitask in that they model a wide distribution and they scale really well. In contrast, we are not able to get this behavior side working as well. So if we think about what we're doing today, and we compare these two different problems, when we try to model behavior, we typically use TD learning. And this scales pretty poorly. The objective is not that stable. Typically, there's some combination of bootstrapping, function approximation, and such. And generally, we find that if you train your agents with the Bellman equation, you really can't use very large models, as I'm sure many of you have seen before. We're really restricted in the types of models we can use before the algorithms start to break down and become unstable. And this really limits the ability to train an agent to be able to perform wide distribution of behaviors and generalize well. In contrast, on this vision and language side, typically we use a very simple objective. For example, in self-supervised learning, just train the log probability of seeing the data. This is nice and stationary and doesn't require these recursive iterations. We've seen that this scales really well. For example, in GPT-3, you just increase the model and you magically get better performance. And in contrast to RL, you're really using these really huge networks nowadays. For example, GPT-3, Dolly, they grow very big. This is, of course, in contrast to RL, where we're really not using bigger models than we were, say, 5 years ago. And we're still operating under like the similar scaling regime. So To sort of answer the question I proposed on the first slide I showed, we believe that what RL and robotics lack compared to these other fields are strong models that will learn and scale well from data. If we had this kind of model, then someone could take a large data set, train a large model, and we'd be able to quickly fine-tune this model on new tasks. And this would be a really powerful behavior algorithm because it would generalize better, it would learn skills in a sample-efficient manner. And if we could train such a model, it would really open up a lot of possibilities for RL. So that's what we'd like to do. So first, let's think about why RL methods scale poorly and how we can try to avoid some of these issues. So a non-exhaustive list here. First, RL, we typically train them in a small environment like Mujoko, and we train them on a single task. So naturally, of course, it's going to generalize poorly to other environment parameters, to other tasks. We don't model a large distribution of behaviors. Typically, we only model the current policy, which represents some distribution over states and actions. And a lot of times when you do training, even on these single task problems, we tend to experience forgetting with respect to our past behavior. And as a result, we need to keep around these large replay buffers. When we learn using the Bellman equation, we suddenly create this non-stationary problem by having this actor and critic constantly changing. And this introduces a lot of instability. And frequently, for instance, in offline RL, we introduce these complex solutions to try and take care of these things. However, they tend not to scale very well, and have their own set of issues. As a result, if we think about other tasks like language, we could model RL in the same framework that works for language, then we'd be able to avoid all these problems. Language is naturally a large distribution of different sentences and different paragraphs. And so depending on what you condition on, for instance, with GPT, depending on your prompt, you can get a large distribution of generated behavior. Again, it's also a stationary problem, and it's a very simple solution. So first, let's ask, how do we do this? So as a background on transformers, since this is not necessarily standard in RL, transformers consist of these self-attention blocks. Basically, we feed in a sequence of n tokens, for instance, words in a sentence. We perform multi-head self-attention on these tokens. Basically, what that means is you compute the similarity of all the tokens to each other, and each token becomes a weighted sum of all the similar tokens. So this allows the different tokens to communicate with each other in this direct associative way. After the self-attention block, we have a feed-forward block shown on blue on the right. This just performs a little bit of extra computation on every token. Finally, these blocks will return a sequence of n tokens in this residual fashion so that we can just stack these as long as we want. So these details are not so important here, but basically, we've seen so far in literature that transformers have emerged as a universal sequence model. It's dominated NLP. We don't even really think about using LSTMs anymore. It's recently gotten strong performance in vision, not quite beating the CNN components, but doing very well. We've seen the new AlphaFold work. It's totally revolutionized protein modeling, and other tasks as well, like music and so on. So the idea here, namely this universal aspect, is that the transformer really works universally on different sequences and scales really well. So if we had a sequence here, then we could use a transformer and we could utilize all the benefits that have worked on these other fields. So first, I'll talk about control as inference here. In fact, we do have a sequence in RL, namely the trajectory. It typically goes something like state action until the end of the episode. And one way of thinking about this sequence is in terms of a graphical model here. So simply based on the environment dynamics, the next state is conditioned on the state and the action in your MDP framework. The limitation of this initial graphical model is it doesn't tell us how to pick A, which is this entire control problem. So as a result, we introduce the notion of an optimality variable called O here. So basically, the point of this construction is that given ST and AT for every column here, OT represents whether or not the action we took was optimal or not. And so the whole idea is that if we can condition on optimality in this Bayes net, then let's try to figure out what action to take here. So just by performing inference on this graph, we can write out this control problem. If you want to see more details, Sergey Levin has a paper on this. So how do we get this into a practical algorithm? So of course, we don't have access to OT just by the reinforcement learning assumption. So instead, we'll replace this optimality variable with the returns to go RT. And this is just the sum of rewards until the end of the episode. So if RT is high, then we might think of OT as being true, that our action was optimal, or if it was low, it wasn't. So in our framework, we'll replace the optimality variables with this returns to go. Then, if we just use this control as inference formulation, calculating out the probability of optimality given the state and action, by Bayes' rule, this is proportional to the probability of the action given the state and optimality. Of course, this is our behavior policy. If we now condition on the returns to go, which we have access to, then this is a practical version for a Markovian environment. If we want to generalize this to partially observed environments, of course, we'll want to give the entire history of the episode. So now this is the natural sequence modeling objective. This is the exact same thing we use in vision and language. What's the next token given the previous tokens of the sequence? So this is nice because now we can use the same autoregressive sequence models that we found to do well in prior work. And we'll just apply the transformer on the trajectory sequence. So one thing to note here is that this formulation, the probability of AT given ST and RT, is actually the same upside down RL framework as Schmieberger's work from 2019. This was a slightly different inspiration than us, actually. But they have sort of the similar supervised learning idea where you avoid TD learning. Our work will focus more on the sequential aspect, which has its own benefits. Okay, so in summary, on the past couple of slides, I've shown that the goal is to learn this general data-driven behavior model. And we're going to do this by formulating RL sequence modeling rather than using the Bellman update optimization that we've done before. There's several benefits of using transformers here. Firstly, they've demonstrated strong performance on many types of sequences, so they might do well on another type of sequence, being the trajectory here. They scale well, which will allow us to bring RL into higher data and bigger model regimes. They can perform long-term credit assignment via the self-attention operation I've shown before, much more directly than an LSTM or a Bellman update. And we can use a lot of the existing investments and engineering that's been made in many code frameworks for transformers and just use the same code and the same clusters and so forth for the same tasks. So in our work, we propose the decision transformer. It's basically the simplest instantiation of the idea I just showed.
Can I interrupt you for a second? Because there is a section, a question in the chat, and it's better, I think, to get it answered quickly. Because Brandon is asking, what is RT? Is RT obtained after executing action or before? And RT is a return to go, as far as I remember, right?
Yeah, it's not too big of a deal, but it's done before executing the action. So for example, R1 will be the episode return.
So that would be a discounted sum of future rewards, right?
Yeah. We don't actually use discounting in this workflow.
Okay, just sum of future rewards.
Yeah. Mm-hmm.
Okay.
Yeah, so our proposed method looks something like this. So again, as I showed before, our sequence looks like RT, ST, AT. RT being the desired return we want, ST being the current state. For images, we use a convolutional embedding first. And the action is like up, down, left, right in Atari, or standard Majoko, continuous action. And then we use a standard autoregressive model. Here we use the GPT-2 architecture. And then we have a linear head that predicts the action AT. So you can sort of see from this diagram, AT minus 1 will condition on ST minus 1 and all the previous tokens. AT conditions on ST and so forth. So this is a pretty natural idea. Next token is predicted from the previous ones. And again, we can use the same code as for language for this transformer. The objective is really simple here. We just simply maximize the log probability of the action given the trajectory up to the current action. So our main result is to look at this performance on offline RL benchmarks. So offline RL is this problem that has been really interesting lately. That given a fixed data set of behavior, no environment interactions, we learn a policy maximizing the return. So this is nice here because this resembles supervised learning in that we just have this data set, and if we perform the stationary optimization, then this is a really nice problem for us. And if we look at our performance here, this is a transformer being in blue. We compare to both TD learning and behavior cloning. On these three different set of environments, we look at Atari, Jim, and Key to Door, which is a mini-grid environment. We get very strong performance compared to these traditional methods. Notably, TD learning is the current best model-free TD learning method, conservative Q learning. And behavior coding is basically the same thing as system transformer, but you don't condition on the returns to go. You just predict the action. So what we find is that even though we don't perform Bellman updates or any of this iterative algorithms that we've been using in RL for years, we still perform as well as the best model-free offline RL methods, simply using this supervised loss. In fact, on some sparse environments like Key to Door, we actually perform much better as a result of this credit assignment property of the transformer. One of the big ideas in this work is that we model the action conditionally given the return to go. To visualize this, here we plot on the x-axis the target return, so the return we want to achieve in the episode, and on the y-axis we plot the achieved return in the episode. So if we are like perfect in achieving the reward that we condition on, then we get this green line in the middle. What we find is that the decision transformer can actually do quite well on a lot of these environments. If you condition on a return that's higher, the performance will go up, which is of course nice, but also it follows the green line quite well on some of the environments. One of the really interesting things on these environments is that sometimes, for example, on Sequest, the decision transformer can actually even extrapolate beyond the best trajectory in the data set, which is a pretty interesting behavior. So this is important, right? Because initially I talked about how traditional reinforcement learning is a single task problem that's prone to catastrophic forgetting. But here what we have is a model that conditions on the desired returns to model a large distribution. Again, talking about this a little bit more, we're moving to this conditional sequence modeling regime from the standard one-task policy regime. And what we have is a transformer modeling a distribution, and you can access different parts of the distribution through conditioning. So why does this matter? If we use this transformer, then we might be able to be able to train in powerful multitask settings and learn many different behaviors in many different environments, which enable large-scale pre-training and then eventually sample-efficient downstream fine-tuning. For one example of this, we find that if you learn to do many tasks, basically training as a multitask model, this can also help you learn a single task. So to see this, we'll consider this percentile behavior cloning, where basically we run behavior cloning on only the top percent of trajectories in the data set. So generally, you might think of behavior cloning as a weakness. It clones everything, not just the good actions. But here, we'll just clone the good actions. This is the baseline most people don't run. We find it's quite strong. But basically what we're saying is that the decision transformer can also condition to be in the top X%. But what we want to see is that the rest of the data is helping in providing generalization here. So on Atari, the results look something like this. The decision transformer is on the left. And if we compare the numbers to these different percentile behavior cloning, what we find is that even though they're both basically conditioning on the top percent of the data set, the decision transformer outperforms percentile behavior cloning. And this is telling us that this multitask objective and this multitask training is helping even if you want to do one task. And this is really the goal of like multitask training, large-scale pre-training, is that we could quickly learn a new task even from limited data. One thing to note is that we only find these results on Atari. We didn't find this on the GIM environments. Probably, we think, because GIM is sort of saturated in performance there. But that's a caveat for this result.
Can I jump in?
Mm-hmm.
How could it happen that 100% behavior cloning gives you better rewards than 10% behavior cloning for breakout?
Yeah, so for Atari, we found that the Atari task was quite hard because the data was pretty limited relative to the diversity of like the environment. So what ended up happening was that 100% behavior cloning was doing better because it was just learning to generalize better. On GIM, if you look at the corresponding tables, then actually the 10% behavior cloning is the strongest. Sort of because GIM is a much easier environment with less diverse states.
Okay, so in 10% behavior cloning, essentially we had strategies that were only good for the kind of situation that we were in, right? And they were terrible. They transferred terribly to other situations.
Yeah, basically the data set was like shrinking faster than the skills were improving.
Okay, got it. Thank you.
Yeah. Okay, so finally, just some auxiliary results. You can also see our paper if you want to learn more. As I briefly mentioned earlier, we found on some tasks, this transformer can extrapolate a little bit, which is pretty interesting because this suggests a supervised objective. We also find that using sequence modeling and a longer context length improves performance on Atari. This is pretty interesting because you might think of Atari as it's fine just to use frame stacking and you get good performance, but actually a longer context length does help us. On sparse reward tasks, decision transformer can perform long-term credit assignment well, both on key to door and a sparse version of GIM. On a more conceptual note, we don't use like value pessimism or behavior regularization unlike other offline RL methods. This keeps our method simple, it works, and it doesn't really deal with the problems that would result if you tried to scale, for instance, behavior regularization. Finally, and there was sort of this question earlier, if we use return to go conditioning, we actually don't need to discount. Discounting is kind of undesirable because it sort of artificially changes your MDP into something else. Generally, you need it because in order to perform the Bellman backup and have your value function converge, you need to discount. But when you do return to go conditioning, you really just say, I want to achieve this many rewards in the rest of the episode. And you don't do any kind of bootstrapping. So you don't have this recursive equation that leads you to require discounting. So again, if you want to see more about any of these experiments, feel free to look at our paper. To reflect on what we started this talk, we identified the following weaknesses of RL. We eliminated by the small-scale training, poor modeling of large distributions, non-stationarity, and these complex solutions. And when we introduced the transformer, we really were able to avoid all these questions. So the big takeaway I want you to take away from our work is that we can really scale a simple solution. And if we formulate RL sequence modeling, we can probably get more scaling behavior out of our models, even for this behavior task, which is very different than language or vision. So the future of RL, our perspective, what we want out of our agents is that they learn from arbitrary experience, offline or online. They learn from a multimodal data set, vision, language, and so forth. And they model a large distribution of behaviors. And what we find with Decision Transformer, we believe that our work sort of provides some evidence that transformers can learn from this offline data effectively. We can use the same model architecture, the same training objective that has been applied to multimodal problems. So we can easily integrate other modalities. And we can use a single large model for multitask learning. And so sort of looking at this, the cake idea from Yan LeCun, we believe that using some kind of decision transformer style architecture can lead to a lot of advances in reinforcement learning. So I'm sure you've seen this elsewhere, but if you want to learn more, feel free to contact us. And of course, we'll be answering questions now.
Thank you very much. It looks like Abhinay has been raising his or her hand for a while.
Yes, thank you. Thank you, Vadim. Thank you, Kevin. The question, I'm first of all, disclaimer, I'm completely new to reinforcement learning, so I do not know much about it. But let me, ask you this question: is that what is the input and output to the transformer that you have provided the sequence, right? The state, reward, and action. Such sequences from like say how long ago, like what is the length of this sequence and what is the output of the transformer that you are measuring the cross entropy against?
Yeah, so the inputs would be the states, actions, and
Yes.
target returns.
Yes.
The output would be the actions.
Yes.
So the cross entropy would be measured against the actions in the data set.
Right. So
the sequence length we use here, we use like the last 20 or 50 or so
yes.
Time steps in the episode.
Yes.
I think Michael actually talked about using a much longer sequence length.
Correct.
Yeah.
So my question is that isn't the value important? I mean, other than the immediate reward, for example, you are trying to optimize the immediate reward, but what if the overall, how do you bring that into this transformer framework, this value question, where the overall policy is more important than the individual rewards?
So we're conditioning on the returns to go, which is like the value function.
Correct. On the value function or on the rewards, you are only measuring the rewards at every step, right? At every state and action, you are measuring
the RT is the rewards to go, so it's the sum of all future rewards.
I'm sorry. Thank you. And the second quick question is that how about the probabilistic outcomes? When you are in a state and you take an action, that you go to another state with some probability, not deterministic.
Yeah. So in our work, we don't deal with this. However, if you were to model a distribution over outcomes, for example, you do this in language all the time, you learn like next word probabilities, and I think this model would be able to handle these situations.
Thank you very much. Great. Thank you.
Before we have more questions, I'd like to encourage Michael and Kyung to also give their opinion if you have, because obviously you probably have opinions on a lot of the same questions. And There is a question in the chat from Gregory. The model is asked to reach a given reward to go, but it doesn't attempt to maximize the reward in classical RL. Is a decision transformer going to find a policy that provides the shortest path to reach the given reward to go?
Yeah, so this is interesting question. For us, we generally just condition on the expert reward. So of course, this requires knowing what that is. So this is sort of a limitation. Our goal is really to model a distribution of returns. And if we can do this perfectly, then of course, we'd be able to just condition whatever return we want. There are some sort of practical ways you could do this. For instance, in our paper, we show an environment where you can compute the shortest path on a graph. And basically what you would do to get the shortest path is just condition on like as high of a reward as possible. But yeah, this is a limitation that would need some thought to address.
And do you see the chat, right? Do I need to read the question?
Yeah. So the question is whether the policy is meaningful when the traded data is a random walk. So yeah, so we do train on random walks for a couple of the experiments in the paper. So the policy that you get is like optimal or is at least pretty good. So I think the intuition would be that the transformer can model like all the random walks by the returns that they achieve. So if you select a particular return at test time, then it would like go into the model and pick out like the type of trajectory that would give you that return from the random walk. So the question, how would you derive the policy after transformer training? It will only provide the next best action given the previous n steps. How about mapping from states to actions as the output? So in general, you just need to keep around the history of what you did before. So you start with your target return, like the expert return, for instance, and the starting environment state. You output the action. Then you would decrement the target return by the reward. You get the new state, you get the new action, and you just keep on doing this for the rest of the episode. There's also some pseudocode in the paper, if that would make this more clear.
Thank you.
Do you think that relative positional encoding for transformers would benefit in this setting? So here, I sort of glossed over this, but we use the positional encoding equal to the episode time step. So like episode time step 0, we have a particular positional encoding time step 1 and so forth. So this is how we're getting our positional information. I think possibly for really long episodes, you might gain something out of relative positional encoding. It just seems like something that'd be nice to try, but I don't think it's a particularly important idea here.
Yeah, thanks. Yeah, there's a question from me, which is, you have to. So obviously, with this with this architecture, you have to decide which reward you want, right? And you have to condition on the target reward. And if this kind of architectures become the main architecture in reinforcement learning, then we'll probably see like a new science pop up on how to determine what is the best reward in the environment, because that's not always obvious, right? You have to first determine what is the best environment and then condition on it. So how would you solve that problem? How did you solve that problem? Did you think about this?
Yeah. So on the gym experiments, we just use like the expert return. So of course, I guess this requires knowing what that is. Practically, generally, you don't really get much better than the maximum value in the data set, just because this becomes an extrapolation problem. So if you just condition on the maximum value on the data set, this is like quite a strong performance. It's higher than a lot of RL algorithms achieve. So this is the simplest way of doing it. In the future, I think of course you need some environment interactions. You're not really going to do true offline RL. So if you sweep over this, then you can find some level of performance that works for you. I also think that in a lot of the settings, like in a real world practical setting, there's some performance that's acceptable or not acceptable to you. So if you can write this down, for example, self-driving, you have some speed you want to go at. If you're trying to pick in place, you want to be able to move these objects to where you want. So I think in a lot of cases, you probably should have some concept of the type of reward you'd be looking for as well.
Okay, thanks. Well, I definitely agree that this problem only exists for some environment, right? And even in OpenAI Gym, some environments have just a defined reward range. But it's an interesting problem for these kinds of environments where it exists.
Yeah, I think it sort of depends exactly your perspective on the problem. I guess we sort of treated this a little bit more as behavior modeling. But if you treat RL more as an optimizer, then this problem would come up more in that you're looking for the best solution, I suppose.
Yeah, definitely. And this solution where you condition on the best reward in the data set, it really makes it hard to do online RL, right? Because you need to find this behavior first that gives you the best reward.
Yeah, so far in a couple other works and also some preliminary experience on our end, it seems doing 1.1 times the maximum reward you've seen so far seems like a reasonable idea to do. Yeah, it's pretty interesting to think about.
Okay, thanks. So we have another talk coming up by Michael and Kyung. If anyone else have comments or questions on this yet, feel free to jump in. All right, then we'll have some more time for questions in the end, and then now I will give the floor to Michael and possibly Kyung if he's here.
All right. Can you see and hear me?
I hear you loud and clear, and I see both you and your slide.
All right, great. Yeah, so I probably won't be able to see the messages being sent in the chat panel. So if there are any questions during this presentation, feel free to just speak up. My name is Michael, and I am here with my co-author Colin, and we are here to round out the discussion on sequence modeling for reinforcement learning. In particular, we're going to be talking about a model that we call the trajectory transformer. The high-level motivation of this model is actually pretty similar to that of the decision transformer. So now that you're all familiar with the context, I'll make sure to speed up the intro a little bit. I'll then talk about this model and framework and tell some stories at the end that didn't make it into the paper that I think reflect how these two works you're hearing about today might fit into a bigger picture. There's this shared dream that I think a lot of deep learning researchers have. And sometimes it goes as unspoken, but it does underpin a lot of research happening right now. And the dream is that we want to build learning systems that are only limited by the data that we give them. This is a useful property because if we need to improve our system, we always have a boring but reliable way of doing so. And that is just to collect more data. And I think we're witnessing this dream actually panning out right now in unsupervised and self-supervised learning. Language models can write you a passable essay on any topic of your choosing. Contrastive learning can get you useful signals from enormous collections of data, and so on. So there seems to be something of a consensus that we actually have uncovered a class of models that might just keep improving as they see more of the world, at least in the regimes that we're currently training in. The same cannot be said of reinforcement learning, at least not yet. And a lot of good work is being done in this area, but when we try to apply algorithms developed on small scale problems to larger practical problems, it gets a lot hairier. And these are the same problems that Kevin alluded to. So what we want to ask is whether we can apply the lessons learned in unsupervised learning to reinforcement learning and data-driven control more broadly. Now, of course, this might seem like a type error at first, because the goals of unsupervised learning in RL are just plainly different. And it's reasonable to believe that one of the problem statements is genuinely harder than the other. That is true, but you can massage the RL problem into something that looks a whole lot like sequence modeling. And the idea is that we treat the trajectory data that RL algorithms train on as a largely unstructured sequence of states, actions, and rewards. We can then apply the tools of contemporary sequence modeling, namely a big transformer, and train it to model the distribution of these trajectory sequences. There's no special precedence given to rewards versus states or actions. Everything is just part of a sequence we would like to model. There's also no Markov property built in. I'm showing one transition here, but before this or after this, it just continues, and there are more states, actions, and rewards interleaved. In the event of continuous states, we simply discretize each dimension naively using a uniform grid. And so far, there's nothing special done to make this more suitable for RL. It really is just sequence modeling applied to trajectory data. One easy way to probe whether this approach can do anything reasonable is to evaluate it like one would a dynamics model. Of course, there are a lot of extra things going on with this transformer, but what's nice about this diagnostic is that it gives you a very quick signal of whether the architecture is viable without having to worry about a full control pipeline, just because sample trajectories are easy to spot check for reasonability. It is worth mentioning that even though this is a simplified diagnostic, it's not a trivial one. Predicting long horizon trajectories for state spaces of any moderately large dimensionality is not something we can do particularly well. And while learned dynamics models tend to have great single step accuracy, the error in the predictions compound over the course of a trajectory, making long rollouts from these models effectively useless. This is incidentally why a lot of modern model-based RL algorithms now resemble a very old technique called DINA, in which short model rollouts are used to provide extra data for an otherwise model-free learner. This is in contrast to something that looks more like trajectory optimization, which would usually require much longer prediction horizons. And this is all really just because long horizon prediction is so hard. Sort of surprisingly, this issue just does not seem to exist when using a transformer as a dynamics model, or at least not to nearly the same extent that I would normally expect to see it. The two models that generated the rollouts on these slides were both trained on data collected by a reference humanoid running policy. And while the single step model at the top gives maybe acrobatic but physically implausible predictions within a few dozen steps, the trajectory transformers rollouts are visually indistinguishable from actual trajectories collected in the real environment by the policy interacting. What's kind of funny about this result is that I'm not actually sure how shocking it should be. Viewed from the lens of contemporary sequence modeling, where it's possible to generate entire essays seeded from some initial sequence, maybe this is all to be expected. But it is rather counterintuitive from the perspective of how we normally build dynamics models for continuous control and what we can usually expect from them. To get a better sense of why this works so well, we can also be a little more quantitative about it. On this slide, I'm estimating the distribution over the entire trajectory for each model when initialized from a fixed starting state, and using that to evaluate the log likelihood of the true trajectories collected by the reference policy from that same state. So you can think of this as like a validation loss for the models, but done in a way that reflects how the model will actually be used instead of the regular single step loss. The standard dynamics model, here shown in gray, has a pretty nasty drop off in likelihood with the horizon. And I actually had to reduce the range of the x-axis on this plot because the likelihood drop off is so fast with these models. In contrast, the transformer's single step likelihood is slightly better. That's the value at t equals 0. But far more importantly, the likelihood stays high during the rollout. Like I mentioned, the model is discretized, and the way we evaluate the likelihood from the transformer is by treating its predictions from each discrete bucket as uniform over the continuous interval that they cover. This imposes an upper bound on the likelihood, which would correspond to a model that predicted the exact correct token at each step in the trajectory with maximum probability. And we call this the Oracle discretized model, and it's just a useful point of reference. So I'm putting that at the top as the dashed line. This plot does leave us with a question, though, because the dynamics of the humanoid are Markovian. So it's a little bit unclear at first what benefits a non-Markovian model would bring to this task. Because in principle, you shouldn't need a longer history to make state predictions. And I think the reason has more to do with specific architectural decisions than really anything else. One way we know this is by restricting the context window of the transformer so that it only takes as input the immediate preceding state in action when predicting next states. And we can think of this as a sort of Markovian trajectory transformer. And this performs just as well. It's also possible that the discretization is doing some of the heavy lifting, with the intuition being that classification could be easier than regression. We tried adapting the transformer to predict continuous states using Gaussian heads instead of the standard output, but this worked no better than the regular single-step dynamics model. There are, of course, some caveats in here, though, and that this isn't a true negative result, indicating that it's impossible to make a continuous trajectory transformer work. It really just means we couldn't figure out how. And that's probably just because the default transformer architecture is so well oiled at this point that we got more mileage out of contorting the data to fit the model by discretizing it than by adapting the model to better match the continuous data we were given. That all being said, even though the long horizon conditioning on transformers isn't required in Markovian environments, it actually does make a difference in POM-DPs, as we would expect and hope. The takeaway here is that the longer context windows don't really seem to hurt anywhere, and in some situations, they're genuinely necessary, so we opted to just leave them in across the board. There is another common way of probing these types of language models, and that's by looking at the intermediate self-attention weights. You might have seen these sorts of plots in machine translations, where they're used to show how these models know how to transpose word orderings between things like subject-object-verb languages and subject-verb-object languages. And we can do the exact same thing here to see which input tokens are most strongly influencing which output tokens. We find really only two salient strategies. The first, which I'm showing on the left, looks like a learned Markov property, in which the model's predictions primarily depend on the immediately preceding state in action only. This makes a lot of sense, I think, given the prediction results. We know that the long horizon conditioning doesn't seem to hurt, even when it's not strictly necessary. So it's probably not too surprising that the model is learned to be Markovian in some situations. The second is a little more interesting. Each dimension of the state prediction depends most strongly on the corresponding dimensions of all previous states, giving it this overall striated appearance. And then the actions most strongly depend on previous actions. Now, this is weird because it violates our usual intuition about how modeling a behavior policy would work, and that we normally think of the actions as being a function of the previous states. But actions depending on actions actually is reminiscent of something that's done in some trajectory optimization algorithms called action smoothing, which is used to ensure that action sequences slowly vary. Okay, that's all for the diagnostics and the visualizations. As promised, we're going to use this thing for control as well. The short version is that we use beam search, which is just the go-to heuristic search algorithm used to decode neural language models. If you aren't familiar with it, it basically boils down to maintaining a set of promising search candidates to hedge against situations where greedy decoding is not the right approach. The absolute simplest thing you can do is use beam search to sample a probable trajectory under your data distribution. This is the standard use case in language model decoding, so it just requires absolutely no modifications. If you enact the first action from the sample trajectory and then rinse and repeat this whole process after you go to a new state, you turn this into a receding horizon controller. We evaluate this in terms of its ability to clone expert policies in some locomotion environments and also some more complicated kitchen cooking and dexterous manipulation tasks. Here we show standard behavior cloning in red, and our method, which we're referring to as transformer trajectory optimization, is in blue. In reality, given enough data coverage, standard behavior cloning is actually a pretty hard baseline to beat, but we see that in some of the harder environments, we do get slightly improved performance. And I think there are probably two subtle differences between what we're doing and the usual BC implementation that explain this. The first is that we're optimizing for entire trajectories to match those of the reference policy instead of only modeling the immediate actions. So you could say this is like a long horizon model-based variant of imitation learning. The second difference is more a consequence of the model than beam search, but it ends up being important in practice. Standard implementations of behavior cloning with a stochastic policy usually use Gaussian policies, but our parameterization is more expressive due to the transformer's autoregressive discretization. So what that means is that we'll be better at modeling data that was collected by humans, or in particular, any data that didn't come itself from a Gaussian policy. And this is the case in, I think, the kitchen environment, for which the data all comes from human demonstrations. In the imitation setting, all the sample trajectories are conditioned only on previous states and actions. This happens with what's called a causal attention mask. In language modeling, the causal mask just refers to the fact that it is generating sentences in left to right reading order, but the name is actually even more fitting for predicting dynamics because it reflects this kind of physical causality of the past determining the future and not the other way around. That being said, all of the relevant conditional probabilities are still perfectly well defined if we do condition on something that happens in the future. So now we can do what we call anti-causal conditioning, where we condition samples on a start state and a target goal state. This is, at an implementation level, very reminiscent of things like upside down RL or the return conditioning done in decision transformers that we just heard about. And this just immediately gives you a goal reaching method. So in the figure on this slide, I'm showing some sample trajectories that are conditioned on a black start state and a blue goal state after training on data collected in this four rooms environment, one of the classic RL benchmarks. And finally, we can do regular good old RL reward maximization. The general idea here is that beam search by default maximizes the log probability of generated sequences, but we can replace log probabilities with really any other sort of cumulant that we want. So we can swap in the predicted rewards and use beam search to maximize the sum of rewards instead. As an aside, under the controller's inference framework, the reward signal denotes the log probability that a transition is optimal. This actually has a neat interpretation as replacing the log probability of a transition with its log optimality, but then using the same sort of heuristic search technique to perform inference. Because sequence modeling for RL is best suited to situations where there exists a lot of prior data to train on. We make the same experimental decision and evaluate in the offline RL setting. The yellow bar here corresponds to standard behavior cloning, just a sanity check baseline. I'm then showing two of the best performing model-based offline RL methods. Conservative Q learning, or CQL, is the state-of-the-art model-free method right now, or at least as of the time of writing this paper. And our method, once again denoted as trajectory or transformer trajectory optimization, or TTO, is on the far right in blue. The conclusion from looking at this plot shouldn't be that transformers unambiguously beat every other RL algorithm out there right now. This is the sort of situation where implementation level details and hyperparameter tuning are going to change the particular ranking of a lot of these methods, given how tight some of the margins are. The importance, I think, is that these methods that we're comparing to are the result of a lot of collective effort and tuning to get conventional offline RL algorithms working. So the fact that you can throw more or less the standard tools of language modeling at the same problem with very minimal modifications and get the same kind of performance, I think is a decent sign that this direction could be a fruitful one. I do want to be careful, though. I think there's a risk of sending the wrong message here. One thing you could take away from the last slide, which is not true, is that beam search is some sort of up-and-coming trajectory optimizer, and this is just not the case. In reality, beam search is not a particularly great search technique. But when your model's good enough and you have a bias to keep the samples in distribution over a rollout, I think it just doesn't matter all that much. Standard model-based methods don't usually use a data-driven sampling distribution for action proposals. And the issue with this is that it leads you to querying the model at a lot of out-of-distribution actions. Because we model the states and actions and all parts of the trajectory jointly, we don't run into this issue. And that's probably the real reason we get away with beam search. All right, that is the trajectory transformers paper. One of the great things about seminars like this is that you get to tell stories that didn't make it into the paper, though. So I wanted to close by giving something closer to the actual backstory of how this project came about. I really just wanted a better dynamics model. I was working on model-based RL, and I was becoming disillusioned because I thought there was very little hope of getting control with models to work when we couldn't even reliably predict with models. And this sort of result from one of my first slides was the sort of thing I was bashing my head against. And this was happening around the same time the GPT was writing entire essays given a seed sentence. And I started wondering why they didn't run into the same issues. After all, the generated essay is a sequence of tokens, right? And that's kind of like a model rollout in a discrete state space. So I crudely pattern matched to the success story there and tried a transformer architecture as a dynamics model. And it just worked far better than I could reasonably expect it to. So this was originally going to be used in a pipeline that looked a lot more like standard trajectory optimization. And that's where the name transformer trajectory optimization comes from. But we then realized we could take all of the extra moving pieces like reward prediction and action proposal distributions and also stick them into the sequence model. And what we ended up with was actually more interesting. It wasn't just a better dynamics model in an existing model-based RL algorithm. The whole RL algorithm had actually been reduced to sequence generation. I tell this story because I think it was a very different starting point from where the decision transformer began, but we converged to a pretty similar conclusion. Of course, sometimes your starting point can give you blind spots. Because our algorithm started as a model-based trajectory optimizer, it never occurred to us to simply not predict future states and only use them as inputs. That's a really, really clean and practical design decision that I think makes a lot of sense from some vantage points, but it's one we missed because of our particular vantage point. What this also means is that even though the high-level ideas are similar, the methods aren't actually as close as one might expect from the titles and abstracts alone. And these are really the types of differences that would normally make or break an RL algorithm. But both of our implementations seem to be roughly on par with the best prior dedicated offline RL algorithms. So I think really the main takeaway is that something about this idea really just wants to work. And it's robust enough that it can be realized in very different ways and still turn out fine. And that makes me excited to see what we can do next by thinking about RL from the lens of sequence modeling. Thank you for inviting us to this seminar. I want to give one last shout out to my co-authors on this work, Colin and Sergey. And Colin is also on this call to join for the Q&A.
Yeah, great. Thank you very much. There are a few questions in the chat. Do you want me to read them or?
Oh, sure. I will switch back to the meeting screen and open up chat as well.
And then there are a few
Is the first one
questions
from Gregory?
Yeah. Yes.
Let's see. I'll read. Yeah. My experience was the same as what Kevin meant. Oh, sorry. The question is, how do decision transformers and trajectory transformers compare to RL in terms of compute requirements? I found that training the trajectory transformer on the just offline RL benchmarks converged faster than the standard Q-learning based approaches. I think this has maybe something to do with how well tuned the transformer architecture is, or maybe just that supervised learning is easier to get to tune right. But I did find the training to be much faster. What was a lot slower for us was actually planning with the model, because if you want to plan using long rollouts, that's obviously much more costly computationally than just doing a single forward pass of a small MLP policy.
Yes, this runs into something I wanted to ask. So how long is actually one step in this framework? Because you have to plan with beam search, right? So is it feasible for something like a robot or something that has to take decisions all the time?
How long is in like wall clock time?
Yeah, pretty much.
Right now, no. Right now, I think we are like at least an order of magnitude off from what you would need to do like online control with this sort of model in any realistic control setting where you're acting with any reasonable control frequency. One thing that I could say, which I might buy into, is that because we really didn't make any effort to turn this into an online algorithm, I think after we now fix a working trajectory transformer algorithm and want to speed it up, I think there are probably some decent ways of doing that. It just wasn't really the goal of this paper. But yeah, right now it is not a good online real-time controller.
Yeah, that definitely looks like the consequence of your history, right? You wanted a model and you ended up with a good model. But then to make it make decisions, you have to actually do beam search and other long things.
Exactly. One saving grace is that so we didn't go this deep into some of the architectural details, but we're using a pretty small transformer compared to the models that are used in big language modeling. And we didn't tune this extensively, but I have a hunch that you could actually make the model architecture a lot smaller, and for some robotic control tasks retain most of the performance, and that would give you a pretty big speed up already. Do you want to add anything to that, Colin?
Can you guys hear me?
Yes, we do.
Okay, yeah. So something I want to add is that currently we're using like autoregressive discretization, which could be another factor that we could improve upon, which is basically that we're predicting each individual state, autoregressive, individual component of the state and action autoregressively. And something like parallel generation or other method that could really speed up the whole planning process, because like we might not need to plan in each individual states, each individual component, which can be really slow. And it could also potentially reduce the kind of the window context length that we will need to do, which will probably allows us to scale to much larger architecture.
Yeah, thank you. Yeah, really interesting. Yeah, I'd like to repeat that I encourage everyone to, both presenters and like attendees, to give their opinions if you have any. Yeah, so there is another question from Gregory here on data efficiency. He expects
that was kind of the same as the first question. The efficiency means, of course, fitting the policy. So this has been well and answered by both presenters. The second one is about generating data. So how many episodes would you need to train reinforcement learning or these decision transformers? I would assume that the decision transformers using data from a demonstration policy is more efficient with data. This is especially important when you have real-world environments which are very complex, where generating the data might be very, very slow, and having the need of less data becomes critical. So the question is, well, I guess I can look at the details in the papers on how many episodes were used for training the two different models.
This is a really good question. I think I think the big answer is that there is probably a trade-off between like efficiency with respect to amount of training data and with respect to amount of test time computation needed and flexibility. So I think if you only ever have a single reward function in an environment and you only ever want to act with respect to that reward, then you probably don't need to do the type of trajectory optimization that the trajectory transformer does. It probably is overkill because you can amortize all that work by just conditioning on the thing you want to happen. I think the real benefit of doing something like trajectory optimization is that it allows you to optimize for things at test time that you never actually train for, or that aren't easy to specify given a single conditioning input. So for example, you can condition on rewards and you can condition on target states. But if you take our 2D like 4 rooms environment and you want to condition on a target state, but also at test time avoid some information, avoid some region which has become dangerous, but it wasn't dangerous in training, that's something you could do with this sampling trajectory-based approach that you wouldn't really be able to do otherwise. So I think it's about how much flexibility you need at test time, and the more flexibility you need, the more computationally expensive your operations will be. As a more practical but maybe also important note, you could imagine combining these things where you do return conditioning or goal conditioning to that handles most of the work at test time, and that looks a lot like decision transformer. And then when you run into an unfamiliar situation, you revert to planning. So it would be like a modification that you don't always need to invoke, or a subroutine that you don't always need to invoke, which is when you get into unfamiliar territory.
Yeah, thanks. Brian has a great question about common crawl for RL. Like, what would be a data set that we would train the big important RL model that everyone is going to use on?
I have to admit first, what is common? I'm not familiar with common crawl. What is that?
That's a language data set that's used for all of the language models, for a lot of the language models. It's just a huge corpus that you can train language models on.
Gotcha.
Yeah, because that's really something, I think that is really a big difference between RL and language. So we are trying to, we are looking for transformers to make the same breakthrough in RL as they did in language, right? But in language, we have one task, which is language modeling, right? Predict the next word in the sentence. And this one task is used as the source tasks for any kind of transfer learning. right? So we can have OpenAI or Google train one model for us and spend like $1 million in training this one model, and then we will use it for transfer learning to all other language tasks. And I don't exactly see this in reinforcement learning. We have to train it for concrete environments, and that would make it a lot more expensive. So the question then is, can we try to replicate the idea of common crawl in reinforcement learning? Is there a way to train a model that's generic enough that we can then use for transfer learning?
Yeah, I think you see this in like the history of a lot of successes in machine learning and deep learning in particular, where the data sets have to come before the algorithm development, or they have to exist for us to actually be able to differentiate between these algorithms. And I think we are in some kind of important way right now benchmark bottlenecks in reinforcement learning, where we're very saturated on the types of things that are easy to evaluate on, things like Mujoko Gym or Atari. And these are things that we've been able to do for a few years. And now we can do them better and with different problem settings, like the offline problem setting. But in reality, these are things we now know how to solve. But we really need like a more complicated RL data set that allows for easy evaluation. And I think there are lots of groups interested in this kind of thing, but I'm not sure if there is a great answer right now for what that data set should be if we wanted to go and test on it. It might have to be something that we'd, have to collect ourselves. I'd be very interested in hearing from the other authors, though, about what you think the right application of this is.
In my mind, I think you really need to restrict yourself to like some class of environments. For instance, the most natural class of environments is real-world robotics. So a lot of times we've seen like things in simulation don't necessarily transfer to the real world and vice versa. So I think in a sense, we won't have a model that does well in the real world and on Atari and on Minecraft and all of these things. But I think if you had a lab and you had enough robots and you had, for instance, unsupervised exploration algorithms, you could collect a lot of data and experience on robots, and you can transfer things like physics understanding, even if you can't transfer things like action spaces. I don't have a great way of how to get there, but I think this is what it would look like.
Yeah, there's a lot of interesting work in meta reinforcement learning, right, where the reward is part of the observation and the agent is trained on different environments. So the resulting model has to be able to not just solve the environment, but also realize what kind of environment it's in and then make a decision. So maybe the answer is just like meta data set from a lot of environments. This is definitely something we haven't solved at the moment. Okay, are we? Looks like we lost Michael and Colin. Oh, okay.
Hello?
You're back. Yeah, we lost you too.
Yeah, I'm still here, even if my video goes out for a second.
Oh, okay, nice. So yes, maybe the answer is meta reinforcement learning and solving many environments with one model. But definitely, I think Bryden is getting to a problem that we haven't solved in reinforcement learning.
Yeah, and I think it's an interesting question whether what you're talking about requires a meta reinforcement learning algorithm, or it will just kind of look like the meta reinforcement learning problem statement, but we apply largely self-supervised techniques to crack that. Because there's a possibility that when training at a large scale with these scalable and stable algorithms, that we can do the kinds of things that people want to do with meta learning, even though there's no explicit meta learning module or meta learning component to it. So I do think the goal will look something like that. But we'll see whether or not the algorithms need to be there as well. And it's possible, but we'll have to scale it up and find out.
Yeah, definitely. Definitely. Okay. Have more questions? There's Sadlow asking about associativity. Do you think that memorizing parts of trajectories, maybe only actions or states, may help connecting such large RL model with generating perceiving models from NLP and vision?
Привет.
Yo.
Yes, I think the line starts to look very blurred in the way that we're training these models. It looks a lot like, the way you would apply the exact same architectures to language modeling or vision tasks. So the architecture is looking the same. The training objective is looking the same. So yeah, I think there is a convergence of tools here.
Definitely. And as far as the next question goes, are there any experiments where NLP generation is recast as an RL problem? There definitely are. I have seen them. It's basically whenever you don't have...
Ты вообще не слышал?
We need
Да,
to
блин,
mute you,
короче,
Leonid. How do we do
Да не,
that?
наоборот. Ну, они дали там, типа, вот эти стейшены, эти экшены просто вообще на форму запихали.
Mute. Done. Sorry for that. Yeah, so I've definitely seen examples where NLP text generation is treated as an RL problem. It is. You can actually test chatbots on people where the reaction is your reinforcement. So the chatbot says something to the person, and whether the reaction is the one we want is the reward. Do you have anything to add?
Yeah, I just want to add that I've also seen RL being applied to provide better generation results, because like beam search sometimes might not give like good examples, even though it's like kind of like a really great way to get good sequence with high likelihood. So there's a way to reformulate this autoregressive generation problem as like RL problem. So there will be like RL agent that selects next token, and we kind of like train to have like good generation quality.
Yeah, I also had a more technical question about your paper on positional embeddings. So in Decision Transformer, the positional embeddings are embedding the number of the episode step, right? And do you use positional embeddings, and what do they mean in your case?
We do, and ours are relative. I think actually as asked earlier at the call today. So our positional embeddings don't correspond to the raw episode step, but the position in the model rollout. So if it's the first step in your rollout, that gets effectively t equals 0, even if you're halfway through your environment simulation episode anyway. I think my general feeling is maybe the same as Kevin's, where it seems like a hyperparameter that could matter a little bit, but probably won't be make or break for either of these algorithms.
Yeah, definitely. But
what do you think, Colin?
I don't have like more to add actually.
Doesn't that sort of it makes it hard to change the size of the rollout, doesn't it? Because theoretically, the model can start performing worse if you trained it on one side of the rollout and you then changed it. Because it's so.
In principle, yes. In practice, it's not. Well, in practice, we just train for the maximum rollout that we're ever going to use. And the reason why we need to do that anyway is because of memory considerations. So eventually the memory will just fill up and you can only fit so much into the context window anyway. So you'll always have to kind of set an artificial maximum, regardless of whether or not you have these positional encodings.
Yeah, okay, got it. Yeah, thanks. I don't think I have any other questions, so who does? Do you have questions to each other? Sadlow is asking about what kind of common RL tasks may benefit from extremely long episodic history.
I think for this question, like partially observed environments such as mazes would come up here. This is not really something we look into. Again, like Atari, you can really do this just by looking at the past couple frames. But for example, on our sparse reward tasks, key to door, we found like logger history, of course, is necessary in order to be able to handle sparse interactions. In this case, at some point, you're going to run out of memory, probably somewhere around 1,000 time steps. So if you have a long environment and a trajectory length longer than this, it's probably worth considering this linear transformer architectures.
Absolutely. All right. So does sound like the questions are drying up. So shall we wrap this up? I'd like to thank everyone who joined. I definitely learned a lot. Hopefully you did as well.
Thank you for the invitation.
Thanks for the invitation.
Thank you.
All right. Then I guess this is then for today. Hopefully we'll see some of you at our further seminars. We usually do them every 2 weeks. And yep, see you around.